Our next topic is joint, marginal and conditional densities and CDFs, and for that we shall need some notions from multivariate calculus. You are going to learn all these multivariate calculus results rigorously in your Analysis 3 course, but for now I will give you a brief primer of the barest minimum that we are going to use. When we work with a function from R to R, the so-called univariate function, that is a single variable, then we like to visualize them as their graph. Now when we work with a function from R2 to R, which are called bivariate functions, then also we can think of them as graphs, but now the graphs will be on the xy plane. Earlier the graph was drawn on the x-axis. Here it is on the xy plane and the graph will look like a surface. So if I take any point xy here, then the height of the surface above that point gives you the value of fxy. When thinking about a univariate function, we talk about continuity, like it is continuous here, you can draw it without lifting your pen, but here there is a hole, so discontinuity, here there is a jump, and here you are going towards infinity. So these are the different cases of discontinuity, and you can have more exotic types of discontinuity as well in univariate case. In case of bivariate thing, the surface must not have any hole in it or any jump or any cut in order to be a continuous function. So that is how you visualize different types of discontinuities, and here also there may be more exotic types of discontinuities that you cannot really draw in a picture. When you want to think rigorously, in case of univariate thing, you can think in it in terms of limits. When x approaches a point A, fx should approach the corresponding value fa. That means it is continuous at A. The same thing is true even for bivariate case. This is your function and here is a point AB. I will say that this function is continuous at AB if whenever I take any point, say here, and I consider the value of the function above it, then when I let this point approach this point in whatever way, it can even spiral down to it, come like this, go like this, but eventually it must come close to it, then this point will also come close to that point. If this happens, then we will say that it is continuous. So mathematically we can write it as when xy approaches AB, fxy approaches fab. In the univariate case, we say that a function is differentiable at a point if in the graph it is smooth, which means that if you look locally, it looks like a straight line, and that straight line is not vertical like this. Here it does not look smooth, there is a corner, so it is not differentiable there. I have taken a point A and here is the corresponding point. I can see it is smooth, so I can approximate it with a straight line, the tangent, and any such straight line passing through A, FA and not vertical has the general form y equals fa plus m times x minus a. So this m is the only thing that I need to specify this. I already had my a and had my graph function f. This m is called the derivative of f at a. Precisely the same idea occurs for multivariate functions also. I am going to illustrate with a bivariate case. So I have a function of fx comma y. So this is the surface. I have taken a point in the xy plane a comma b. The corresponding point on the surface is a comma b comma fab. I can see it looks smooth, so I know it is differentiable. In this case, looking smooth means it can be approximated with a plane. So when you look at only a neighborhood of the point, the surface just looks like this particular plane. Now any plane that passes through this point, and this plane must not be vertical, has the equation z equals fab, z is the vertical axis, plus m1 times x minus a plus m2 times y minus b, which is very similar to the univariate formula. So this plane is uniquely determined by these two numbers, these two slopes, slope along x direction and slope along y direction. So it is only natural that we define the derivative of the function at this point using these two numbers, and it is common to express these two numbers as a 1 cross 2 matrix, first m1 then m2, and we call it the derivative matrix or grad of f. So that is the term which we use for derivative in this case. Now it is seen that if fxy is differentiable at the point AB, then m1 is this thing, del f by del x evaluated at AB, and m2 is del f del y evaluated at AB. In case you do not know these notations, let me quickly explain with an example. Suppose fxy is x square y plus x, then when I want to compute del f del x, I just differentiate with respect to x holding y a constant. So when I differentiate this, y is a constant, so this thing becomes 2x and y is a constant. In this case, plus x becomes just 1. Similarly, when I compute del f by del y, I hold x as constant, so this just becomes x squared, y has been differentiated out, and there is no y here, so it is just nothing. So del f by del f del y is x squared, del f del x is this. And when I put in place of x equal to a, in place of y equal to b, I get this thing. Just a word of warning here, I said if this holds, then this holds. However, the reverse thing does not hold, the converse does not hold. Even if these two partial derivatives exist, these are called partial derivatives, that does not imply that fxy will be differentiable. If differentiable, then they must exist, but they may exist even if it is not differentiable. We shall also need to use quantities like this, which is nothing other than del x of del f del y. That is, you take this del f del y and now you differentiate partially with respect to x. So in this case it is x square, anyway there is no y. So this will just be 2x. Similarly, you can define the order as reversed. So this is equal to, so now you start with this and differentiate this with respect to y partially. So when I differentiate this partially with respect to y, 2x behaves as a constant and y. So it is 2x plus 1, that vanishes. You notice that these two things turn out to be the same, and that's what happens most of the time. There are pathological examples where it will not occur, but in most cases, in fact in all the cases that we shall handle in this course, we will always see that these two things are same. And incidentally, these two things are called mixed partial derivative because we are mixing x and y. For this fxy e to the power xy square, compute these two partial derivatives and these two mixed partial derivatives and check if the mixed partials are equal or not.